Welcome to our brief overview of data management for data science. Today we'll explore the fundamentals of Python programming, a crucial skill for managing and analyzing data effectively. Python's simplicity and versatility make it a favorite among data scientists for tasks ranging from data cleaning to complex analytics. We'll cover the basics to get you started on your data science journey, so let's get started. Assuming that you have some understanding of Java, let us compare the key similarities and differences between Python and Java. Here is a fun fact. Both Python and Java are implemented using the language C. Each one brings features that make programming easier and more secure. First, regarding data typing, Python is dynamically typed, while Java is statically typed. This means we do not need to worry about defining data types in Python. Second, Python is an interpreted language, meaning that code is interpreted and executed in real time, unlike Java, where the code is converted to bytecode. Python is slow compared to Java. Both languages do automatic garbage collection. For more sophisticated programs, Python may not support multiple threads running concurrently. Both languages are cross-platform, providing flexibility. Python has become quite popular due to advances in data science and AI, as it provides a rich library of code. Python is easy to learn, which is why many universities now use Python as the first language. Next, we're exploring variable declaration and type systems in programming. In Python, we enjoy the flexibility of dynamic typing. This means you don't need to declare a variable type. Python figures it out for you. This can speed up development, but requires careful testing to avoid type-related errors. On the other hand, Java uses static typing. Here you must declare the variable type explicitly, like int or string. This ensures type safety and can catch errors at compile time, but it requires a bit more upfront work. Understanding these differences is crucial for effective programming in each language. Iterations are critical in any language for repeating a set of instructions. Say you want to iterate through a list, you have a list of things here and you would go through each one element at a time. This is great for processing a list of names, for example. We can also iterate through a continuous range of numbers. In this case, range 5 will deal with the numbers from 0 to 4. This can be useful if you'd like to iterate a fixed number of times. A while loop allows one to iterate without knowing how many iterations are needed. As long as the while condition is true, the loop runs. For example, imagine going to an ATM and completing a number of transactions without knowing how many in advance. Now, let's explore conditionals in Python. We'll start with if-else, if statements which allow your program to execute different code blocks based on various conditions. Then we have ternary conditionals, which offer a more concise way to write simple if-else statements in a single line. Next, we'll discuss nested conditionals, where you place one conditional inside another to handle more complex decision-making processes. Lastly, we'll touch on checking membership in a list, which is crucial for determining if a specific element is present within a list. We will use these constructs in future programming assignments. Next, let's dive into some advanced topics very briefly, of course. In Python, type safety is a bit of a double-edged sword. Unlike some other languages, Python infers types at runtime, offering flexibility but potentially leading to errors that only appear when the code runs. This means you might not catch type-related issues during development. However, this flexibility allows for powerful polymorphism. Functions can operate on various object types as long as those objects have compatible methods or attributes. This can make Python code versatile and expressive, but it also requires careful testing to avoid runtime surprises. In Python, variables don't store data directly. Instead, they hold references to objects. Think of variables as labels pointing to data stored elsewhere in memory. This setup allows Python's garbage collector to automatically manage memory. It keeps track of object references, and when an object is no longer referenced, it's marked for deletion, freeing up memory. You can even interact with this process using the GC module for more control. Understanding these concepts helps make your code efficient and memory smart. Mutable data types are things that can be changed. Mutable types like lists, dictionaries, and sets can be changed after they're created, allowing for flexibility in data handling. On the other hand, immutable types such as integers, strings, and tuples cannot be altered once they're set. This distinction affects how you manage data updates. While you can reassign variables to new objects, the original object's ability to change depends on its mutability. Remember, mutable types offer adaptability, but immutable types provide stability and predictability in your code. Let's visit Python's variable scoping rules, specifically the LEB rule local, enclosing, global, and built-in Python. When you define a function, the variables created inside it are local to that function. This means they can't be accessed outside it unless you specify them as global or non-local. Python uses dynamic scoping to determine where you can access a variable. The LEB rule helps Python figure out which variable you're referring to at any given point. Start from the innermost scope local and expand outward to built-in. Understanding this hierarchy is essential for effective Python programming and avoiding those pesky scope-related bugs. In Python, there's no need for explicit variable declarations or initializations. Like in some other languages, a variable springs into existence the moment you assign it a value. But here's the catch. If you try to access a variable before giving it a value, Python will throw a name error. This flexibility allows for cleaner and more dynamic code, but it also places the responsibility on us as programmers to ensure every variable is properly assigned before use. Keep this in mind to avoid those pesky errors. So that was a brief intro to Python constructs. We will develop more programs to make these topics more clear while identifying challenges in debugging Python code. See you at the next video.